Hi, everybody. We are going to wait about 1 minute while everybody joins, but thanks for coming today. So just to say hello to everyone, thanks for jumping in. We're going to wait about another 30 seconds. It takes a little while for everybody to get on, and then we'll get going. So welcome. Okay, welcome to guests and panelists today. Good morning. I'm James Bullock. I'm the Dean of the School of Physical Sciences. I want to thank everybody for showing up early this morning. Today's program is in honor of Earth Day, and we're thrilled to be able to bring you some of the school's thought leaders to talk about the environment. This series is called Compelling Conversations. Typically, it's an exclusive virtual opportunity for the school's partners. But today we are opening up to everybody in honor of Earth Day, and I think it's going to be a live and fun event. So this is unscripted. We're just going to be talking to each other, and what we found in the past is this can be a lot of fun. If you want to participate in the conversation, you can go ahead and use that Q&A button down there, and we will be able to see those questions, and I'll try to interject those in whenever I can. If you want to support events like this or the research that we're going to hear about today, you can do that via texting. You can text the letters PSCC to the number 41444. Okay, so let's go ahead and get started. First, I want to introduce quickly our panelists. First, Don Blake. So Don is a distinguished professor in the Department of Chemistry. He has also held a joint appointment in the Department of Earth System Science here at UCI. Professor Blake's research focuses on atmospheric chemistry. He studies the composition of the Earth's atmosphere in remote locations throughout the Pacific region, from Alaska to New Zealand. He also studies the air in highly polluted cities throughout the world. Among the many things he's well known for, he was among the first, or maybe the first, to show that methane levels were rising. Methane is a greenhouse gas, and we're aware that CO2 is going up. At the time he was originally studying this, people thought that was going to be constant, but it's now widely recognized that it's going up, and it's going up from human activity. We'll probably hear a bit more about his thoughts on methane later today. I'll also mention that he won the Better World Award from the UCI Academic Senate this year. This award recognizes a research career filled with positive societal impact. So welcome, Don. He holds a BS in chemistry from UCLA and a PhD in chemistry from UCI, where his thesis advisor was the Nobel laureate Sherry Rowland, the founding chair. And we will hear, I'm sure, a bit about that experience and Sherry's legacy today as well. Next, we have Eric Saltzman, who's also a distinguished professor, this time in the Department of Earth System Science here at UCI. Professor Saltzman studies how biosphere-atmosphere-human interactions affect tropospheric oxidation. He's interested in the history of trace gas and climate interactions. He does this partially studying air bubbles and aerosols that are trapped in deep polar ice cores from Greenland and Antarctica. He has one of the coolest labs to visit on campus because there are all these amazing ice cores. And I think if you're nice to him, you will sometimes be able to get a drink with some tens of thousands of year-old ice in it if you're super nice. He's an expert in the production and emission of atmospheric chemistry on ocean trace gases as well. He served as the head of Arctic science for the NSF in the Obama administration, and I think for some of the Trump administration. We'll probably hear about that later. He has a BS in geology from the University of Rochester and a PhD in marine and atmospheric sciences from the University of Miami. And finally, Paulo Brando, an assistant professor in the Department of Earth System Science. His research relies on field work, mostly the Amazon, also ecological modeling and remote sensing to explore the vulnerability of terrestrial ecosystems to repeated disturbances and prolonged degradation caused by human activities and extreme climate events. He has testified in front of the National Congress of Brazil about Amazon deforestation and fires. He also regularly collaborates with policy-oriented NGOs like the Woodwell Climate Research Center, where he's a visiting scientist, to disseminate scientific findings about land use change and climate change. He holds a BS in forestry from the University of Sao Paulo and a PhD in interdisciplinary ecology from the University of Florida. Okay, with those welcomes, hopefully I will talk a lot less from now on, and we're going to start the conversation. What I'm going to do now is I'm going to ask each of our panelists to talk to us in your own words, how you got to this moment, what you're working on now, and a little bit about your trajectory and expertise. So whatever you want to share would be great. So Don, why don't you start us off? What are you thinking about right now, and how did you get here?
Well, as you can see in my background behind me there, that is a photo taken 51 years ago today, on Earth Day. And I don't think many of us thought that Earth Day was going to be more than one time. In 1970, that was it. But it's amazing that it has become such a big and wonderful event. At that time, I was interested in the environment, but I was not a very good student. And so it was many years later when I came to Irvine and worked with Sherry, and Sherry taught us or suggested to us that if we could choose a topic or topics that had a positive impact on the environment and on people, that he encouraged us to follow that route. And so having worked with Sherry, and he led by example. And so as advisors go, he was wonderful in that regard. Lots of different opportunities. I started when the ozone, he and Mario had already suggested that CFCs could destroy stratospheric ozone. But it was interesting for me to watch him, because I saw him as a scientist, and yet a lot of what he did was talk to the public, talk to at the Senate, and he was on TV a lot, and he was quite good at that. And it was a sort of a paradigm shift for me, because I had thought that scientists pretty much stayed in the lab and did the work, and then let others take that. But Sherry was a leader, or a pioneer, I should say, in that. And now we all find, I mean, Eric and Paolo and I, we find ourselves asked questions by the public, and asked questions once again. I mean, Eric being at NSF for 3 years. So being a scientist, the definition has changed a lot since Don Blake was in this picture 51 years ago. I'll stop at that.
Don, that's great. We'll hear more from you in a bit, but thanks. That's great. Eric, why don't you go ahead and go next? Anything you want to say, introduce yourself, etc.
Sure. Like Don, I was a terrible student and an aimless young person, wandering around. I was in the Bronx in the 1960s. And when I think back to what launched me in the direction I ended up, I think about two things that I was aware of in the background. So one was Rachel Carson, this book, Silent Spring, which was the book about DDT and how it was ubiquitous in environments, and how it was migrating through the food chain and causing large-scale disturbances. And the other was this prediction by a guy named Hubbard that we were about to reach peak oil. Peak oil was going to happen in, I think, 1972 or something like that. And from there, we were going to be running out of oil. And both of those things, in sort of my vague adolescent perception, were giving me and a lot of other young people the feeling that the planet was finite. It wasn't a limited resource that would just go on forever. And I think we had kind of, as a society, sort of assumed that it was all out there for us and it would be there forever. So I went off to university thinking about these things, but no idea what to do about it. And I stumbled into a class on planetary science. And in the process began to think, oh, yeah, the Earth is a planet. We think about other planets in a planetary, holistic way, try to understand them. Why don't we try to understand this planet? But nobody was talking about that at the time. So this was a long time ago. And so I began to think global Earth science is a thing, and maybe we should work on that, or I should think about that, but no idea how to do it. I explored geology. You mentioned I have a geology degree, but geology was focused on resource extraction. Geology was about how to get oil and minerals out of the planet, not about how to understand the whole system. Today we would call, we could look at Paolo and say, oh, look, there's a global biogeochemist. And we'd say, we recognize that, that's what we need. But at the time, that word didn't exist, nor did any programs to do it. So I went off and did a PhD in oceanography, where I stumbled into atmospheric science and discovered that we knew almost nothing about the exchange of gases between the ocean and the atmosphere. And that became sort of the theme for my later career, was trying to understand what the oceans and atmosphere exchange and how and why, and how does that affect the history of our atmosphere and the planet. So that's it.
Eric, thanks. So Paulo, why don't you go next? Tell us a little bit about your trajectory and what you're working on.
Yeah, I think the only reason I work in ecology and conservation of tropical forests is because I was not tall enough to become a basketball player. So I tried really hard, didn't work. So then I started moving around and trying to study a little bit. And I moved to Canada, and I look when I was doing my undergrad, and from Canada, I look at Brazil and South America, and I saw how big the Amazon was. And that was a big change for me. And I started studying tropical forests when I was in Canada, which is kind of odd. And then one day I just sent an email to this big scientist studying how tropical forests work. And he never responded. So I wrote it again, and then he never responded. So I wrote it again, and then he responded. So I moved to the Amazon for 3.5 years. And that was fantastic because he was just a great scientist. Daniel Napstead, he is a great scientist. And with him, I learned a lot about to understand what we're losing, or to know, quantify what we're losing in terms of biodiversity, ecosystem services, tropical forests. We have to understand the system. So I got fascinated to understand this really complex systems that is behind it. You know, 1 hectare of a forest, like an area of a block, in one of our plots, we had close to 400 tree species, for example. That is fantastic. And I think in my research, looking back, you know, a couple of moments in my career or my life, I said, okay, why did I get into this really to understand nature? And there's a question that George Woodwell, the founder of the Woodwell Research Climate Center, asked once, and he, a journalist from the Washington Post, giving a talk in one of the seminars, and it was, what is the boundary of your subjectivity when you do your news, when you write your story? And I thought a lot about this, and the boundary of my subjectivity is that I think forests are awesome. They're important for our lives. They're important for us, for our society, for a bunch of different things. And my research tried to disprove that. And what is left, I think, is very important contributions for conservation. And that's, I think, one of the most important topics that you can study today if you're thinking about sustainability of our society. But there are two things I would like to mention. One is, when I was a kid, 9 years old, Chico Mendes was murdered to try to save the Amazonian forest. He was a rubber tapper in the state of Acre, living there, and farmers started to cut down the forest that he extracted resources from. And I think he became one of those big leaderships to show the world of what was happening in the Amazon at that time, when we didn't have good satellites, we didn't have good information, we didn't have internet. So he was doing it all, right? Coming from the forest, and he was just showing the world what was happening in the Amazon and touching people's heart. Today, we don't need that satellite or him to show us. We know, we can see from space. But we need people like him to touch people's hearts, right? To really connect what is happening with the science and how that can improve people's lives or avoid a bit of the destruction that we see today. Anyways, but I'm gonna stop right there. And another thing that I think is awesome in the science at UCI that allows us to really bridge this policy gap, right? Connect science with policy. And to that, I've been part of the United Nations report on the Amazon status. So, and also to talk with a lot of policymakers, how to translate science into policy.
Thanks so much, Paulo. So I'm going to now, I guess, turn to people and just start asking you about some things you've been involved in. And then we can just use that as a jumping off point. Don, you know, I mentioned methane in the introduction, and I know that you've been involved in landfills or worked on landfills and the use in methane reduction and with the UC. Can you tell us a little bit about that story and how it fits in with this global concern about climate?
Yes, well, There are many greenhouse gases. I mean, CO2 is one of them, methane is another, N2O, and there are others. And they all contribute to this holding in of energy, if you will. And if we go back 50 years ago, methane, as you'd mentioned, was thought to be constant in the atmosphere. And so why study it? And I asked that question to myself, not to Sherry. Sherry said, study it. So the fact that methane, in fact, was not constant, that it was going up. And back in the late 70s, early 80s, it was going up at about 1% per year. And so this was a big deal. And it ended up making it so that methane was the second most important greenhouse gas in terms of impact since 1960, let's say. So methane is a knob. We have different things that we can do. And Paulo was working, on Brazil and trying to, well, I don't want to, he'll tell you better than I can, but trying to save some or all of the forest, because it plays a huge role in the world's ecosystems. But methane is something that if we were to cut back on methane emissions, we could have an impact on, we could reduce greenhouse gases some. And so I didn't fall into this, but one area I remember back in the 80s, I think it was Paul Crutzen, who was also one of the three who won the Nobel Prize in 1995. I was with Sherry Rowland, and Paul sort of had this wonderful way about him, sort of this wonderful smile. And he says, there's another methane source, we think. And Sherry said, what? And Paul said, landfills. And so I remember that. I don't know how much Paul did other than maybe think this up or whatever, but landfills are thought to be maybe 10% of the sources of methane in the atmosphere. And so we were involved with a study of the University of California Office of the President, where a landfill down in Shreveport, Louisiana, was paid for by the University of California Office of the President to improve its infrastructure, to put a different cap on it and so on, and to actually turn some of the methane that was escaping into gas that was actually sold to the local gas distributor. And the amount of methane that was reduced was on the order of maybe 10,000 tons of methane per year just from that one site. And so there's a push, at least some of us are pushing, to encourage UCOP to look at other landfills to see, first of all, if they're emitting much. If they're not emitting much methane, then they're not a problem. Because methane is on its own is a more important greenhouse gas per molecule or per mass than CO2. And so by reducing the amount of methane that's going in the atmosphere, you are getting more bang for your buck, if you will. And so anyway, I'm hopeful that this landfill turns out to be something that at least University of California and other places in the United States try and purchase, not credits, but actually go in and improve the infrastructure and reduce raw emissions of methane into the atmosphere. So it's very exciting, because once again, almost 50 years ago, Sherry was saying that methane was constant, and I felt sort of, when your advisor tells you to do something, you do it. And I was somewhat frustrated, because it's like, well, why am I measuring if it's not changing? And now 50 years later, we're on to something that might actually allow us to have an impact other than just reporting that methane was increasing. Now it's like, well, look, we think there's there's swamps, there's rice paddies, there's cattle, lots of sources of methane. And I think they all deserve to be addressed in a rigorous way. So I'll stop at that.
Thanks, Don. That's interesting. And I like this idea. You talked about knobs that you would turn, and one of the knobs we could turn is methane. And I want to talk more about that. But since you mentioned Paulo, I want to give him a chance to sort of talk about what they're trying to do, because I think there's an issue that sometimes it's easier not to spill the milk than it is to clean it up after you spilled it. And I think that that's related a little bit to what's going on with the Amazon. I don't know if I did a good job with that or not, but Paula, why don't you say something about what's happening? Why is the Amazon so important, and what role does it play in global climate?
Yeah, so it's super important. We are in a key moment in Amazon conservation. We had this very rapid change happening in the 80s and 90s and early 2000s. So with thousands and thousands square kilometers of forest being cleared, mostly for pasture lands, and in a process that involved a lot of land grabbing, speculation, people stealing land, and in 2008 we saw a decline in deforestation in the Amazon, 80% decline in deforestation, all the way to 2013, and not a lot of increase all the way to 2015. So that was what I call the period of hope, because there were several actors and several elements coming together to allow for that major reduction in deforestation. And one of them is just to make protected areas more protected, making sure that the big companies colonizing the Amazon in many ways are held accountable, and a couple other different elements. And then suddenly we start seeing this very important build up on that. Yes, that's the future. The future is the Amazon standing without much deforestation. It is taking care of our global climate system, so we do not push the system over the edge. It's already pretty hot in this region, so if we get even hotter, maybe the trees are going to die. So let's be careful with our climate system. And if this forest should die, all of a sudden we'd have worth of 10 years worth of global climate emissions. All this wood going into the atmosphere as CO2. So it'd have a big impact on our climate system, not to mention all the water cycling. These trees here, they can put roots that are 50 feet deep. So that is super important. But then since 2015, we see, or 14, there's more increase in deforestation. And then there's a jump in 2019, in 2020. And it's a bit with this dismantling a bit of the basis that allows us to reduce deforestation by 80%. And there's almost 20% of the Amazon now cleared, mostly for cattle ranching. And the big question is, will this forest survive with the mountain pressure that are put in upon them? We're changing climate, we are changing land use, we're creating more of the edges that are super hot near these agricultural fields. We're reducing the amount of animals in the landscape. And we are creating more thunderstorms, convective storms that can interact with some of these edges and kill trees. And so there are all these elements converging to maybe push this forest over the edge. And we don't know exactly where this edge is, but it's clear that it's really important to know how much change is too much to the system. So a lot of the research is like, okay, let's try to save some of these forests, of course, and see the importance of saving this forest, but also some of the elements that allow us to do that. And I think the research is a bit of like how much beating this forest can take before it turns into something else. And I think right now it's a key moment because it's this turning point. We went from this period of hope, and how you're entering a phase of new expectations. We have to get our act together in order to reverse that back. So I'm going to stop there.
Thanks, Paulo. So we have a question that I'll just ask, and then there's a couple other things building up. We'll get to all the questions in the Q&A eventually, but there's a question just about the political situation in Brazil. I mean, are there leaders that are doing anything about it? And I know you're involved in this quite extensively. Maybe tell people a little bit about what things are like right now in Brazil.
Yeah, in 2019, it was kind of a very messy year because we saw fires in a lot of places, and including the Amazon, and there's a lot of confusion what it was burning and why it was burning. And if you go back, you see that deforestation was increasing, and if people deforest clear land, there will be fire because people just burn all the wood. that they cleared. So we saw that happening, and there was a lot of denial of what was happening. And we can see from space now. So there's no way to deny. But they managed to deny the demonstration a bit. But then when they burn all that, the huge bonfire, I think the biggest bonfire on the planet that was created in 2019 and 2020, it was pretty clear that there's a major issue there. And on the one hand, you see this dismantling of the environmental agencies in Brazil right now, weakening at least of those agencies. But in 2019, there's a bit of this wedge, right, that we could work on in terms of to save a bit of the Amazon, or at least strengthen the conservation in the region. That it is the producers and farmers and the different business people to work to reduce deforestation for 20 years, remove the deforestation taint from their food supply chain to export to Europe and other places. They do not want to be associated with land grabbers, with thieves, with people who are violent, stealing land. And right now, this government is sort of putting the two of them together, and there's a lot of backlash in trying to do that. So I think there's an opportunity there just to say, okay, we need the good guys actually getting more incentives because they're doing the right thing, and the bad guys just being sort of punished for the crimes they commit. And I think there's a business opportunity there a bit to resolve the situation. Other than that,
can I ask?
Yeah, go ahead.
So to this Earth Day, there was a lot of pronouncements from different nations about what they're going to commit to and so forth. And Brazil's commitment was to reduce illegal deforestation, right? So how do you see that in the context of the last year? Do you see that as this trend that you're talking about of the trying to tease apart the two pressures?
No, it's a very beautiful paper to say we are going to reduce deforestation, but the problem is that we don't see a plan on how to do that. If you say one thing and then you do another thing, you fire people who are really good with the enforcement, who are very good professionals in creating the policies that lead to less deforestation. If you go after the head of the space agency and fire because that head of the space agency said, there is deforestation. So there's all these elements that say, okay, if you look at the facts, they are not going towards that goal. So it's very good that there's a statement put out there, but it'd be really nice from now on to see a plan and how to reduce that illegal deforestation with the actions that have been taken over the past year and a half. So if those actions change, and one that was very interesting, there's a law passed that it is for payment for environmental services. And we can measure that really well from ESS in our department. And so if there's a payment for that, that's great. So let's go for it. But it's really nice if you could see the plan lay out so we can evaluate whether it's feasible or not.
So Eric, as a former head of a big government agency, you're looking at Arctic science. What is your perspective just from that vantage point on these related issues? I mean, what was that like? And then maybe as a piece of that, you can tell us a little bit about, what's the future of the Arctic going to be like, and what should we be prepared for?
Okay, I'll just make a sort of a general comment. So I went to the NSF. I spent 2 different periods at the NSF, one very enmeshed in science and another one in management. And the period you're talking about was in management. So I went there to manage this organization, Arctic Science. It was really interesting in many, many different ways. One of the things that struck me, so the Arctic is a special place. It's incredibly complicated. It's a place of boundaries. Everywhere you look is a boundary. There's a sea ice boundary with land, and there's the open water and the sea ice, and then there's the Arctic indigenous nations right up against the Western nations, and then you have Russia right across from the US. It's a place of incredible diversity and closeness, right? It looks big on the map, on a Mercator projection, but the globe gets really small up there and everybody is quite close to each other. So it's a really interesting place, and it's a place where there's no treaty. So the Arctic is a free-for-all. There's this intergovernmental thing called the Arctic Council, but it's not a treaty of the sort that governs the Antarctic region, which is a formal international treaty. So the Arctic is the Wild West. It's really an interesting place. And the science of the Arctic is really interesting and really challenging, both because it's so hard to work there, and also because it's changing so fast. It's changing on a rate. Paolo was talking about dramatic change in the rainforest. The change in sea ice in the Arctic, from a year-to-year basis is just staggering. And so it was interesting in many different dimensions. And I had a lot of interaction with policy types, folks working towards policies relating to the Arctic. And what struck me the most, one thing that struck me was, as a scientist, was that in many cases, the science is clear and has been clear for a long time, that the needs of the policymakers are relatively simple and have been met. Okay, we know that we're on the brink of massive Arctic change, and once that happens, we're not going to recover from that because of the feedbacks in the system, and that sets the policy. From there, it's the will of the policymakers, the ability to convince the public to get behind it, the ability to get international actors and so forth to talk and to move together. So during the Obama administration, there was a lot of will to move forward in these things. There was a lot of effort and progress in a steady sense. That was pretty much ground to a halt when the administration changed. A lot of initiatives were stopped, and I think it's restarting now, and I expect to see more progress coming in the future. It's a hopeful time right now, I think.
So, of course, one of the things that's driving, the main thing that's driving all of this extra melting ultimately is we have these greenhouse gases that are being pumped in the atmosphere. And we have a question here, in which I think we should ask Don, I think is the appropriate person to answer. We're getting questions about, you mentioned that there's many kinds of greenhouse gases. And we just sort of asked, what are the top 5 greenhouse gases and the relative importance? I know it's a little complicated, depends on how long they stay in the atmosphere, but maybe give us the story on that, Don. What should we be thinking about in terms of CO2, methane, et cetera?
Well, Eric had mentioned all these feedbacks, and this is an issue. But I mean, the big one is CO2. Ozone is another one, and ozone is not stratospheric ozone, but tropospheric ozone, and the amount of ozone in the atmosphere, in the lower atmosphere, the troposphere, has increased, we think, maybe by a factor of 2 or 3 over the last 200 years. And so that's just your pollution. Okay, when we think of LA and the pollution, we have haze there, and we also have ozone. And so this ozone just gets mixed. And so the background concentration of ozone are increasing. So actually having reducing urban pollution would slow down, if you will, the amount of ozone that's going into the atmosphere. So urban pollution is and that's something that that is a knob that I think is most easily convincing of people, is that you can look out the window and see smog. Okay. And so to tell people there's smog in LA or in India is a foregone conclusion. To tell them that smog is going to impact climate change in 10 or 20 years from now, that's a tougher nut to crack. And so, but methane is a knob we should be thinking about. N2O is an important one, but it's a slow growth thing, and there's a natural amount of it. There are certain gases, the CFCs, and we go back to what Sherry and Mario did. These are gases that have a greenhouse warming potential that's huge, because they have to absorb in an area of Earth's radiation going out that makes them, 10 or 10,000 times more important on a molecular basis than CO2. Once again, I'm methane centric. I mean, my whole existence in science, it seems, has been on methane, and so I look more at what, there's a lecture at noon by Brenna, who was a former graduate student of mine, talking about different areas of a dairy that could be addressed in terms of methane emissions.
Yeah.
There's fracking. There's oil, gas leakage in urban areas, the pipes or people's homes. So once again, my world is methane, and it seems like within methane, there's the landfills, there's cattle and dairies and things like that can be. I mean, this is sort of like death by 1,000 cuts.
That's interesting, Don. One of the last meetings I went to in Washington before I left was an all-agency meeting on methane. It was to bring together all the science agencies who had an interest in methane and to discuss what's the state of the science, what are the needs that remain, and how can we move forward and get the national knowledge base needed to turn the knob, right? Yes. And so that just seemed like a no-brainer. All the agencies were on board, everyone was ready, and then it stopped. and I think it's restarting now. I think our efforts are restarting, and I think the reduction of methane is going to be a big part of the Biden plan to reach these ambitious targets by 2030.
And another way of looking at not the specific greenhouse gas, but the sectors also. And you asked James about the Amazon and the importance, and it relates a lot to agriculture, what we eat and how we have this global commodity exchange and trades. And so in the Amazon, if you have a cleared forest, usually then you have pasturelands, and then you have soybeans, sometimes corn. And if you have cattle, you have cows eating grass and then burping, and then you have methane being emitted, and it's a huge amount of methane. And then if you have the conversion into soybean, maybe you have another greenhouse gases, and corn especially, you have N2O. So in all of that together, if you combine all that emissions from agriculture, it accounts for about a quarter of all the emissions, global emissions of greenhouse gases. So it's not only pushing deforestation to have a lot of emissions, but also it has to do with how you manage those systems, and that can lead to a lot of greenhouse gas emissions. And what we eat in the US and how we behave in the US will affect that trade system and the pressure to grow more food in the Amazon or use the Amazon more or less sustainably. So it's all interconnected, and that is super important. If people, looking at us now, it's like, what it has to do with the Amazon? Well, the Amazon, what we do in the West affects everyone in the planet, including people in the Amazon.
So that's related, I think, to a question we've got. And, I know this is not 100% everyone's expertise, but what can individuals do? I mean, we talk about, I think there's this issue that I think most people recognize there really does need to be some societal changes in the way we make energy and live our lives in a very big sense. But the question here is more, what can individuals do? I mean, I know there's things like you probably want to electrify your house and not be using gas if you can. Electrification is good. Heat pumps are really particularly good if you have an opportunity to look at those things. But I'm not an expert on these things, but I don't know if you want to add anything about how individual decisions can change, electric cars, et cetera. But I don't know if other people have thoughts.
Yeah, I would say two things: reduce your meat consumption, especially beef, and that is super important. And I would say the other is just to think a lot about when you vote, because that can influence everything else, and most people can do that in the US.
Yeah, voting is critical. As Eric mentioned, sort of the momentum that we had, and then the momentum that we don't have, and now the momentum we're trying to gain it's critical that we have leaders who understand the problems and have administrations that are staffed with people who actually do have not just the United States' best interest in mind, but the world's best interest in mind. And I'll just say that and this will probably cause some discussion here, but the concern when we the question is what can we do? Okay, can you have an electric car? Can you walk to work? These are all things that help. Voting is important. Education. I mean, the last 4 years, science took a beating, in the press at least. You know, I mean, we have alternative facts now, and that was, you know, I don't even know how that's a word. And so being educated, and educating yourself so that you can then communicate with others, not just as scientists, but just common people, to be able to say that you know, I mean, I've seen, since I'm a methane guy, I've seen a lot of jokes and memes about cows and the gas that they give off, you know, and you know, I just want to say, look, you know, 95% of it comes out of their mouth. They burp, you know, this is not, I mean, it all needs to be taken seriously. And we need to convince people that in fact, the temperature records are accurate and the models predict into the future. You know, there are boundary conditions. And so one model, you know, might predict a 1 degree change in global temperatures in the next 100 years. And another one might say it's going to be 3 or 4. And all these systems, you know, how much destruction of the Brazil is going to happen? How much melting of the ice caps? I mean, there's so many things, and that's why there are these ranges on these, you know, these models. And then the problem is that those who are sort of climate deniers, if you will come on and they'll say, well, look, you know, you said it's going to be 5 degrees. There's only 1 degree, so we don't have to worry. It's like, no, that's not, you know, the problem is the sign. The sign for all these predictions is that it's going to get warmer. Okay, it's never a negative sign that things are going to get colder. And so we need this is a huge problem, and we as a world need to work toward.
I would just say, you know, for people wondering about themselves, what can I do? There are a lot of resources on the web, like carbon calculators. You can try to calculate your own greenhouse footprint, climate footprint. And once you see that, you will know immediately, wow, this is where I need to, this is what I need to do. This is where I need to put my effort. And I think there's a lot of resources for that. A lot of good social science and good thinking has gone into how to get people to understand what they themselves can do. And what can we do as a scientific community? I think we're doing it. we're trying to learn, we're trying to understand, we're trying to communicate. And that's.
So we've got a number of questions here, and Paolo, I'll let you go. Let me just say, we've got a number of questions here about large scale engineering solutions and sort of technological solutions to this. We're not going to have time today to talk about those kind of issues, but let me just suggest that you just Google the word solutions that scale, UCI. There's a whole initiative that we've organized around the campus focused on this very issue. And there's actually some talks that are up there that are that have been recorded and given. You can watch them on YouTube about people looking at hydrogen, different ways of trying to solve problems with long haul trucking and other issues. There's a lot of work happening. There's a lot of work at UCI, for example, on carbon capture, et cetera, et cetera. There's a lot of effort in this direction, but it's sort of a lot of things need to happen, unfortunately. But anyway, go ahead, Paolo. I'll let you actually say something useful here.
No, I have more a question for Don and Eric, which is about COVID-19. I think COVID-19 just brought or highlighted the importance of science and knowledge, accumulated sort of the accumulation of knowledge to come up with a solution that in this case is not only the vaccine, but just all the behavior we can take or steps we can take to avoid transmitting the virus to other people. And in our areas, we have our own science community. We know a lot about these issues. We know a lot about the Amazon, what you have to do or not to do if you want a healthy forest, understand about the methane emissions. But most people do not know about this. And I think with COVID, this part of the science was just became the highlight, right? How you produce a vaccine and the science to get there. And everyone is watching that process. But in areas, maybe we don't have all that focus and we don't have all that broad reach. But do you imagine that with this big shift in our lives, the science will have another place in our society in the next few years to bring a more sustainable place?
So I'll give my perspective. I think, when I think about the US over my lifetime, certainly, and post-war US, it's really been a science-driven nation, right? We have led science globally. We have based many policies on science. We have really become a science-driven society. And you see that in the pandemic. We have this vast resource of knowledge and expertise in infectious disease and molecular biology, and it was brought to bear very quickly. And I think we should appreciate what we have. It's an incredible resource, and it has meant incredible things to this country. Every dollar spent on science is a huge multiplier into our societal well-being. And I think there is a deep bipartisan agreement that that is the case in the United States. There has historically been a deep bipartisan agreement that we're a science-based nation. Now, at the same time, the population of our nation is not uniformly in agreement with this. At the same time, we're detecting the first gravity waves ever in history. Board of Eds are telling us that we can't teach evolution in our schools, right? We have anti-vaxxers in one direction, and it's a mess. This is the human condition, and we can't, we shouldn't, I think, ignore the fact that we are still a science-based, nation, even though there are these countercurrents of different things going on. So just one example from the federal government is when the administration changed, and all of a sudden this sort of anti-environmental approach came in. Basic science funding didn't change because there was bipartisan agreement in Congress that we need to support those basic science agencies, and it's important to us. So I think educating the public, like Don said, that's super important. It's important to bring the country with us and the world. But I think the fundamentals are still there. I don't think I don't think it changes the fundamentals.
Yeah. So let me ask, we've got a couple questions here about climate modeling and also, how much do natural phenomena contribute to greenhouse gases, et cetera. I'm sure all three of you have taught, teach about these issues in courses you've taught, but does anyone want to address sort of natural sources versus how well do we understand the climate from a sort of physics standpoint?
I think Eric should go.
Well, let me just look at the specific question.
Well, one is how much a natural phenomena such as volcanoes contribute to greenhouse gases, and a related one I think you could build off is, how well can we model extrapolate into the future with climate simulations, et cetera?
Okay, so volcanoes are not a big player on the sort of timescales that we care about. We really care about what's going to happen in the next 100, maybe if you're a real optimist, the next 1,000 years. That's what we care about. Volcanoes are important in the carbon cycle, but on hundreds of millions of years timescales, and we just don't have to worry about that. Right. And are our models good enough? I think maybe I could just raise that question. Our models are incredible, and they're getting awesomely better all the time. There are some things that I'll say, there are some processes that we know about that we can't do a good job of modeling yet. And I think Paulo will tell you about tipping points, right? There are places where the climate system could get really sensitive that are difficult to model with confidence. So an example of that, classic example today is the ice sheets, right? Sea level rise. Exactly when? We know the ice sheets are melting, some of them are melting, and that sea level rise will happen, but exactly the rate of that sea level rise is a very difficult process to model. So what I've seen, I'm not a climate modeler, but what I've seen over my career is that our models tend to be conservative. We're always using the physics and chemistry that we know to project the future, and those estimates tend to be very conservative. So for example, in terms of ice melt and sea level rise, all the changes in the models are up and up, you know, increasing, becoming less conservative as time goes on. And there are some real nonlinearity, some real tipping points in the climate system, like deep ocean circulation, that have the potential to change climate dramatically that are not in the IPCC climate models that project the next century. So,
and I will mention we have a live event with Eric Rignot later this afternoon that we'll be sharing, and he studies some of these kind of issues and with glacier melt that aren't being included in models. And it's, you know, I think we'll hear a little bit more too from Eric there, but things are accelerating, if anything, beyond.
Can I tell
Sure.
one little story about that? So when I was a young oceanographer, I was working on atmospheric chemistry in the tropics, and I got this great idea that these signals should be in the ice sheets. So within a couple of years, I found myself standing on top of the Greenland ice sheet with another young scientist, a guy named Richard Al, who is today a world famous glaciologist. And so we were two young scientists, you know, and I was asking him everything he knew about ice, because I didn't know anything about ice. I was a tropical oceanographer. And one of the things I wanted to know is, how long does it take to melt an ice sheet? And Richard told me thousands of years, many thousands of years to melt an ice sheet. I said, so we don't have to worry about that? He said, no, don't worry about that. I said, okay. 20 years later, I said, Richard, why did you tell me that? It's because we are all worried about the ice sheets melting today. He goes, oh yeah, he said, that's because we thought it was frozen at the bottom. So 3,000 meters below where we were standing, 2,000 meters, the ice we thought was frozen to the bed. But in fact, it wasn't. It was melting at the bed, and the entire ice sheet can slide. And so 20 years later, 25 years later, we think we can melt an ice sheet in 100 years, or a couple of 100 years. And so the physics that we know today is different than the physics we knew then. And like many other things, it's looking faster than we thought.
And I would just add to this climate simulation that, in my experience, not a super climate modeler, work with the output of these models, but the temperature, right, how the warming, it's not super hard to predict, right? The basics is just physics, right? To have this long wave radiation being trapped into the atmosphere, and that's kind of straightforward. I think what is really tricky is just to identify all the feedbacks in this system. So if you warm too much, will the Amazon collapse? All this carbon go into the atmosphere, and then they have this spiral of death, right? And that is really hard to predict and to model. But I would say that in general, we're conservative because we do not include a lot of these potential processes. Another one is the permafrost, right? The thawing the permafrost. We do not consider the potential effects of putting a couple billion tons or hundreds of billions of tons of carbon in the atmosphere that could come out of the thawing the permafrost. So I would say that we are a bit conservative in terms of how we model the feedbacks of increased temperature and what it would do to our system. So we are, and that is, I think, the really hard part. And the research we do at DSS at the School of Physical Science is super important to know whether the feedbacks are super strong or they're not. And depending on the feedbacks, we may be in a lot of trouble. And, you know, given the example of Eric, yeah, sort of his experience.
So
I'll drag this back to methane for a second, and I mean, since we're talking about feedbacks and stuff, that's a great story, Eric. Is that methane, more than half of methane's sources in the atmosphere, you know, are swamps, rice paddies, and these types of things, and these are all very temperature dependent. And so, you know, the question is that if the temperature rises 2 degrees, what effect is that going to have on the actual output of methane from these rice paddies and swamps? It's a nonlinear process, and so there's so many complications. I mean, the models are getting better, but once again, the question is that are there some feedbacks that we still need to worry about, that we've thought about, but that we aren't sure how to implement?
James, I saw a question there that I thought was really interesting about the removing of greenhouse gases from the atmosphere. I think that's a really interesting question, right? I mean, people talk about that, like we're going to build devices that are going to extract CO2 from the atmosphere. I don't think anyone can do that even close to energy neutral. In other words, it takes more carbon dioxide, more fuel to burn to get the CO2 out than,
Yeah.
So that's a loser.
As a physicist, I can tell you entropy is a hard thing to overcome, but yeah, go ahead.
Right, so that's a very difficult.
I have to disagree with both.
Oh, because of trees. Go ahead.
Right, right.
Yes.
Figured this out. Nature can do this. But man is stuck, I think, at the tailpipe. And so we can build devices that will pull CO2 out of the tailpipe of a car or a factory, the CO2, because it's very highly enriched, it's concentrated. And people are proposing that. There's a lot of funds going into that. But I think the plan is to take that CO2 and pump it back in the ground and extract more fossil fuels, which is kind of a tough road to go in the long run. But of course, trees can do this. And we are not yet smart enough to build a machine that's as good as a tree. But I think there's great work going on in photochemistry and material science that's going to let us build devices that will pull CO2 out of the atmosphere.
Yeah, and just 2 words about this huge, important old machines that can suck carbon out of the atmosphere. There are trees, right? Right now, we have this huge push to restore the biosphere, and that is great, especially for some places where we need soil, we need biodiversity, we need connectivity of the landscape. But you have to keep in mind that, by planting trees, this doesn't mean that we can keep pumping CO2 in the atmosphere and cutting down trees, because it's much more difficult, expensive, everything else to plant new trees than to avoid the loss of this old growth forests that are tall, complex, and store a lot of carbon. So I think that is something that we still have to, I think, do a soul searching, because there's this push for huge restoration, and that is super important for many cases, but it's not the solution, right? Eric, the solution and Don is just to stop pumping CO2 in the atmosphere and to avoiding the deforestation. Otherwise, it doesn't make any sense.
I'll just mention, if you're interested in carbon capture, there's one of the chemists here at UCI named Jenny Yang. Her lab works on carbon capture technology, and her research group has taken over the social media feed of the school yesterday to talk about some of their efforts. And I'm just going to put a link to that in the chat if you're interested in emerging technologies there. But I agree, Eric, the electrochemistry here at UCI is really world class, and the collaborations between engineers and chemists and others is making a lot of progress in that area. So I get to brag about that a little bit. So we've got a couple minutes. I don't know if anyone has closing thoughts. If we want to try to end with a little bit of an uplifting discussion, my thoughts are going to Ralph Cicerone right now, who helped found that department of yours, Eric. And I don't know if you want to say anything about Earth System Science at UCI and those efforts and, and what we're trying to do in that way. Globally.
I would just briefly. So it was a visionary thing to start the Earth System Science Department, and it was started by, Sherry Rowland and some other folks who were already here at UCI, and they brought Ralph Cicerone in to lead the creation of this department. Very, very visionary, and I think very successful. And a lot of the kind of work we've been talking about today has been done there, very successful. I think what's happening now and in the next 20 years is going to be connecting that up with all the strengths across campus. There's just tremendous strengths in the sort of science that's needed for solutions. Solutions are much more complicated things than just identifying the problems. And I think that's where we're going to go as a department and as a school.
Well, that's great. I mean, we're almost out of time. Any final thoughts from folks? Let me just say for the people who are attending, if you want to support this research, please go ahead and do it. Even $10 actually can help us do things that we can't do other ways, it turns out. And so anything is helpful. So Don, Paolo, you want any closing words?
Yeah, thank you. And just say one thing that is really awesome about ESS. I was in Brazil a couple of years back, and then Jim Randerson's group and a couple of people ESS said, look, there's this forecast that the fire season will be really bad in the Amazon. And actually, these results went all the way to the Secretary of Environment, to governors, and they put more resources to firefighters in the Amazon. So it's an amazing research that can have huge positive impact. And I'll just end with that example.
I'll just say that you know, I'm proud to be associated with this, and sort of look back to how Sherry started this whole thing, and that he would be very happy with the progress. Thank you.
Thanks everybody. So this is recorded, and we'll distribute it once it's posted. And so thanks very much. Till next time. Bye bye.